Hey guys, Mr. Smith here, and I'm shooting a video on before class on applications of periodic functions, just so I can get this out there ahead of time, and then for anybody else on the on YouTube who would like to view it. So yeah, today we've done a lot with periodic functions. We looked at we've looked at the kinds of equations that make periodic functions, like the sine function, cosine function, and we've made transformations of those functions, and we've got practice graphing them and determining equations from a graph. And today we're going to do those things, but with an application focus. One interesting application of periodic functions is the tides. I won't bore you with the physics lesson, but we all know the sun exerts like a gravitational tug on the Earth, but so does the moon. And when the moon and sun are lined up, we get a little extra tug from the moon, and we get a little bulge of water on the Earth's surface. It's a little deeper. We call that the high tide. And as the planet rotates through this bulge of water, in a lake or a bay, especially like near the ocean, what you would see is the water getting deeper and then shallower and deeper and shallower. And because we spin through this bulge twice a day, we have these tides repeating every 12 hours. So we have a function here that's modeling with some nice simple round numbers the depth of a bay at a certain point in the Earth. And we're going to model the depth in terms of the time using like a 24-hour time clock. So like t equals 0 would be midnight, t equals 12 is noon, t equals like 13 would be 1 p.m. But we have an equation here, and we're used to making sketches. So let's sketch this periodic function. So I'm going to go through this sort of quickly because we've had a lot of practice graphing at this point. So the axis is 6, the amplitude is 2, the period, I do 360 divided by my value of k, which is 30, gives me 12. And my phase shift left 3 units here because of the plus 3. So let's graph it. So axis of y equals 6. It is optional, but the highest we get is 2 above that, and the lowest we get is 2 below that. So our function is bound between these values. Where should we start our function? Normally we start on the axis, but this time we're going to be shifting left 3 on the axis, but instead of at 0, we're going to go left 3. Okay, and then let's sketch it. So we come back every 12 units. So that would be 3, 8 here, and then 6 and another 6 is here. Between these dots is 1 full cycle. So that means every half I'm going to be coming back. So every 6, I'll come back to the axis. And in between that, I go up and I go down. Halfway we go up, halfway we go down. Okay, and I'll graph it over there too. One more will be right there. All right, not a bad looking graph. But now that we can graph it, we can actually just from our graph answer a lot of questions about this scenario. For example, what time of day does the first high tide occur? Well, the first high tide, when the water is as deep as it gets, it occurs at when t equals 0. And how deep is the water at this point? It's 8 meters deep. I should say t equals 0 is midnight for the time. And what time of day does the first low tide occur? It gets as low as 4 meters at when t equals 6. So t equals 6 at 6 a.m. and it's 4 meters deep. So these are things we can just read right from the graph because the numbers are pretty straightforward, nice and round. The period we found was 12, and in the units in this case would be 12 hours. We get 2 high tides and 2 low tides every day. And when will the next high and low tides occur? Well, it's periodic every 12 hours. So if we add 12 hours to t equals 0, we get t equals 12. That's noon for the high tide. And then if we add 12 to 6, we get t equals, I'll just show that. And that is 18 is 6 p.m. So 12 is noon, another 6 gets us to 6 p.m. And this would be another low tide. And again, we could just see that from the graph as well. All right, so a neat application, nice round numbers though, and we could answer all these questions by just making a graph. Now this doesn't always happen in practice. Sometimes we'll need some algebraic ways to check, to do these kinds of things. So let's continue. The last question had to do with, the moon spinning around the Earth and the Earth rotating, and a lot of things like that are periodic, but a lot of things in not just nature, but in real life can be modeled with periodic functions. So I've made up this kind of gag question. Some fashion is cyclical too. Some things come in style. Some things are in style in the 80s that are now in style now, and then next year something from the 90s might be in style. So in this question, I've said it's the width of tie that kind of fluctuates. Sometimes wide ties are in style, and then sometimes skinny ties are in style. So I've come up with this fictional scenario and said, okay, every 20 years, a necktie comes back in style. The widest tie, which is called the kipper, is 6 inches wide, and the thinnest, the skinny tie, is 2 inches wide. And right now, kipper ties are in fashion. So we've kind of been given some information about that we can use to model the scenario with a periodic function. Let's do it. So to create a model, we'll need the period, so we can determine our value of k. And the period is 20 years. It just says so in the question. And that means our value of k is going to be 360 divided by 20 equal to 18. The amplitude, so if the maximum is 6 and the minimum is 2, well, we can get our amplitude and axis. I'm going to squeeze these things in here. So, and using variables that my class is used to using. So A, we kind of refer to as the amplitude, and we get that by taking the max minus the min and dividing by 2. 4 divided by 2 is 2. And then we get our axis, we use C for that by finding the average of the max and min, and we get 4. And I'm going to just add those to my graph. And this should make a lot of sense, because if the highest we get is 6 and the lowest we get is 2, then our axis should be 4 and our amplitude should be 2. Now, one thing I'd like to do in this question, we're just going to change the current year to 2024. This is when I'm shooting this video. It's when I'm doing this lesson with my class. And one more piece of information that we haven't used yet is that right now, kipper ties are in fashion. Right now, at t equals 0, the kipper tie, the wide tie, is in fashion. So we have a point there. I think we'll actually make a graph first, and then we will come up with an equation for this. So right now, kipper ties are in fashion, and the period is 20 years. So in 20 more years, they will be in fashion again. Halfway between those two maximums, we'll have a minimum. The skinny ties will be in fashion. And then halfway in between those maxes and mins, we're going to be on the axis. And I can continue this pattern and just fill up my graph. We would have one more on the axis here. And I think I can even squeeze in, we'll get a minimum there. Okay. And now we can create a model for this question. So let's use T for tie width. And for years, let's use a Y for this one. All right, so our amplitude is 2. That goes in front. And then sine. And then inside our brackets, we have our K value, which we found was 18. Y, we're going to have a phase shift. I'll fill that in at the very end. And our axis is 4. Now, what is our phase shift? We have options. I'm using a sine function. So normally the sine function starts at the axis at 0 and goes up from there. But this time, that is occurring at t equals 15. Or in our case, the 15th year. So because we're shifted over 15 to the right, I'll have y minus 15. The width of tie that in terms of the years since 2024. So really nothing new that my class hasn't done in this question. Given some information about a periodic function, we made a graph and created a model based on that. One new thing we're going to do with this question, we haven't done yet, and I mentioned this too, is like we're going to find exactly which tie is popular in the year 2100 at the next centennial party. It's not practical for us to extend this graph all the way to the year 2100. Instead, we're going to determine the which tie is popular using our new function. So we're going to find the time, or the width of tie. Now 2100 is 76 years from this year. So we're going to find the width of tie that's popular 76 years from now. And we're going to use our equation. Amplitude was 2. We said the value of k is 18. We're replacing y, the years, with 76 years from now, minus 15 plus 4. All right, so I'm just going to give you my advice for doing this. If you're really comfortable on your scientific calculator, you can do this all in one step. However, I might recommend just doing whatever's inside the sign first. So 76 minus 15 is 61 times 18 is 1098. Plus 4. And now I would say, okay, now you can punch that into your calculator as you see it. So 2 times the sine of 1098 plus 4. So I got about 4.6. And this would be centimeters, I think we said. Inches. I don't really know much about ties. That seems wide for a tie, but we're just going to go with it. It's a fictional problem. So 4.6 inches is the widest tie. And so if we compare that with our little chart there, I think a Kipper tie is 4.5 to 6 inches. So according to our question, the Kipper is back in fashion at the next centennial party. All right, so moving on. So sometimes you might not have a description of here's the maximum, here's the minimum, here's the period. What you just might have is some raw data. So in this question, what we have is the raw data for how the angle that the sun is above the horizon over the course of the day in Inuvik in the Northwest Territories. So we kind of know that when the sun rises, it goes above the horizon. And as the day goes on, it gets higher and higher. And then as the day kind of wanes, it gets lower and lower. And you might know, too, that when you get very far north, sometimes in the year, the sun never actually sets. So that's why in this case, we always have the sun being a little bit above the horizon. But we're going to come up with an angle that models we're going to come up with a function that models the angle above the horizon over the course of an hour in the day. And we're using hour past midnight. Again, so t equals 0 would be midnight, and then so on and so forth. So to determine our amplitude and our axis, we actually have to dig through our raw data, and we have to find where's the maximum value and where's the minimum value. So I can see here that 1.8 is my min, and I can see that 46 is my max. And so that allows me to determine my value of A. I will subtract those and divide by 2. Well, that's 1.8. That's 40. Do I dare do this one in my head? 44.2. I think that's 22.1. And then for C, we find the average of those. 46 plus 1.8 divided by 2, and I think that is 23.9. But I'm going to double check that. 47.8 divided by 2. Yeah, so A and C. K, this is modeling the sun over the course of a day. So the period is going to be 24 hours. And so our value for K is going to be 360 divided by 24, which is equal to 15. And the last thing we need to do is to find a phase shift. Now note, we are making a cosine model, and normally our cosine functions start with a maximum at t equals 0. Where does our data have its first maximum? Our first max, I'll just write out first maximum, is not at t equals 0. Ours occurs at t equals 13. That means our phase shift, our cosine function, has been shifted 13 units to the right. So our phase shift, d equals 13. So when we're making a model of a cosine function, we just have to think about where that first maximum is, and that's our phase shift. So it's pretty slick. And we're ready to go here. So we're making a cosine equation here. Our amplitude, 22.1, times the cosine. Our k value is 15. We said our d value is, should be using t minus 13 plus 23.9. So we've modeled some real-world periodic data with a function. And I thought it'd be interesting just to see how well we did. I have this data already ready to go in Desmos. And let's just actually plot the function we had. So 22.1 times the cosine of 15 x minus 13. And before we panic about the graph, I believe I just have to make the graph in degrees. All right, and look, the function we made seems to fit that data pretty good. So I think we did a nice job there. All right, let's continue. In this last question, so each of the previous questions, we've either relied on a graph to do much of the question, but in practice, you won't always be able to make a graph. The numbers might be too big, or decimal values, or just not work out very nice. It might not be practical to graph. So in this question, I'm going to lay out exactly what we are expected to do with a periodic function using algebra, or just using properties of the function. So the first thing that we should be able to do, given an equation, and this equation models the number of prey in an area. So this usually fluctuates because as like predators are introduced, they kill off the prey. But when there's not enough prey, the predators kind of die out, so the prey comes back. But then when there's a lot of prey, the predators can now have lots to eat, and then their population grows while the prey gets killed off, and it's kind of cyclical like that. So in our situation, we have a model that models the number of prey in terms of the year since 1980. How many years has passed between maximum populations of prey? This is just the period, and to get the period, we just do 360 divided by our k value, which in this case is 90. So our period is 4 years. The second thing we'll be expected to do is use the function to find like a y value, or a value of the dependent variable. Basically just do kind of plug and play. So what was the population in 1990? Well, you just plug in 10. So 250 times the sine of 90, we're doing 10 minus 5, and then plus 500. So my recommendation, again, is do the inside of the sine. Now 10 minus 5 is 5, and 90 times 5 is 450. I can do that in my head. But for this, I will need a calculator for. So 250 times the sine of 450 plus 500 works out to exactly 750 here, but in practice that might not always be a nice round number. All right, something else we're expected to do is find the maximum population. To get the maximum, you just take the amplitude and add it onto the axis. So our axis is 500, and we're adding on that. So that maximum is 750. But when does it occur? So let's do that right now. All right, I've just changed the locations to finish off recording this. So yeah, what was the maximum population? To find a maximum, you take the axis, you add the amplitude. Now, what year did this occur? This is something we haven't yet done without a graph. But here's the idea. I'll make a rough sketch down here. So we're working with a sine function. Sine function starts at 0, 0, goes up, comes back down. And if we think about when does the sine function reach this maximum? Like the sine of what gives you that maximum value of 1? Well, we've learned from several lessons ago, it's 90 degrees. It's when the angle is 90, the sine function reaches the maximum. So when we're trying to find the year or when this maximum occurred, what we do is we take all the stuff inside the sine bracket, everything inside, which in this case is 90 times t minus 5, and we set that equal to 90. Why 90? Is because that's when the sine function reaches a maximum. And then we solve this little equation. So for this one, we can just divide both sides by 90. We get t minus 5 is equal to 1. And then adding 5 to both sides, we get the t equals 6. What year is this? Well, 6 years after the year 1980 would be 1986. Now, of course, we found the period is 4, so this also occurred in 1982 and 1990, but hopefully you get the idea. And we can do the same thing for the minimum population. We take the axis, which was 500, and we subtract the amplitude. The lowest this population gets is 250. And when did this occur? Well, again, we have to ask ourselves, when does the sine function reach this minimum value? And we know this happens at 270 degrees. So if you want to find when a minimum happens, you set the inside of the sine function. And again, here, look at our equation. Here, the inside of our sine function is 90 times t minus 5. Whatever's in there, you set it equal to 270. Why 270? Because that's when the sine function has its first minimum. From here, it's probably simplest for us to divide both sides by 90 again. 270 divided by 90 is equal to 3. And then add 5, we get t equals 8. So this corresponds to the year 1988. Of course, 1984, 1980, every 4 years, we would also have a minimum. All right, so this table kind of encompasses all the things that you should be able to do with a periodic function without using a graph. So this sheet will be a good resource for you as you do some practice. And yeah, that wraps up our video on applications of periodic functions. Hope you guys enjoyed. Take care, and we'll see you soon.